Okay, so let's get started with the next chapter, which is machine learning basics. So machine learning is essentially a form of applied statistics with increased emphasis on the use of computers to statistically estimate complicated functions and a decreased emphasis on proving the confidence intervals around these functions. So there are two central approaches to statistics. One is frequency estimators and Bayesian inference. And most machine learning algorithms can be divided into supervised learning and unsupervised learning. And we describe these examples and everything in this one. So now I just want to say that this chapter is quite lengthy. Let's just say it's about 50 pages or something like that. So 60 to 98, 62, make it, yeah. So it's 70 pages. And and this is my favorite thing, obviously, machine learning. It's quite tasty, if you will, like if you would compare it to food. I mean, the entire book is interesting to me, but this one is just as interesting. So let's move on now. Coming to learning algorithms. So Mitchell provided one of the most famous definitions of machine learning. Said a computer program is said to learn from experience E with respect to some class of task T and performance measure P. If its performance at tasks in T as measured by P improves with experience E. Now, it really looks like a rhyme, doesn't it? It quite rhymes with all the P, T, and E's here. So anyway, so that's the definition by Mitchell. Tom Mitchell, you can find his book on Amazon. It's bought by people even today, as I see. And I mean, it's quite old, I would say. It's not as up to date as this book. So, but it's still regarded as one of the classics of the machine learning books. Nonetheless, so task T, experience E, you should improve your performance at doing task T from experience E. That's what we're going to do as measured by the performance P. So the task can be any of these numerous tasks such as classification with missing inputs, and regression, transcription, machine translation, structured output, anomaly detection, synthesis and sampling, imputation and missing values, denoising, density estimation, or probability mass function estimation. And as the author said, this is in no way the exhaustive list. There could be many more of these. Now, what about the performance? The performance P. So again, let's just try to remind ourselves that this is the first section of this book, of this chapter, learning algorithms, and we just took a look at tasks, and now we're taking a look at performance, and we have error rate. There's the test set and train set. That's about performance, and there's experience, and so machine learning algorithms can be broadly categorized as unsupervised or supervised by what kind of experience they are allowed to have during the learning process. So if they have had some experience on the same task, that would be supervised. If they did not have any experience on that particular type of task, that would be an unsupervised machine learning algorithm. And data points, unsupervised learning algorithms, supervised learning algorithms, there will be a label and there will be a target. So all these are the basics. I'm pretty sure you would have heard it like 1,000 times at least if you're someone who has been interested in these topics. And reinforcement learning, of course, is something where they interact with the environment, and they get feedback from that interact from the environment, and there is a reward and punishment. No, the punishment is usually not present, but it basically like zero reward, or sometimes it can be negative reward, which would be called as punishment. And So if they do the right task, they would get a positive reward. If they don't do well enough, they would get no reward, and reward can be negative as well. So based on the how well they perform the last task, they try to improve, and they reinforce the idea of what's right really. So that would be that, and we move on. One common way of describing a data set is with the design matrix. Design matrix is a matrix containing different example in each row. So each column of the matrix corresponds to a different feature. This would be different example. For instance, the each dataset contains 150 examples with 4 features for each example. So 150 rows, 4 features for each example. This means we can represent the dataset as a matrix X belonging to real numbers 150 times 4, where X I1 with the sepal length of the plant, X I2 sepal length of the plant. So we describe most of the learning algorithms in this book in terms of how they operate on design matrix datasets. So yeah, moving on. So they're going to an example here. It's a linear regression. Now I'm sure like you guys might have heard of this before. Uh, Linear regression, y output is defined as y equals w transpose into x. W is vector of parameters, also called as weights, and x would be the input. And yeah, so we're going to minimize errors using mean squared error displayed here. Now there are lots of kinds of errors, L1 error, L2 error. I think we have explored some of them in the previous chapters. So here we're looking at mean squared error for the test dataset. M is the size of the dataset, and Y will be the output of the test, and Y hat is the real output. Y hat is the predicted output. So hat usually represents something that's been predicted. So and Y is the actual output. So yeah, so there's idea. Y hat would be prediction of the model some test set, and Y will be the actual value. So we're just squaring the difference between the actual value and the predicted value, and we're taking the mean of it by dividing it to the total number of data points, and that would be the mean square error, also called as MSE. Now you can also express it like this in terms of like L2 norm. So you're taking the L2 norm and then squaring it. So there are increases when equal distance between predictions. So to make machine learning algorithm, we algorithm to improve weights. So yeah, so all these derivations, you can go through them. They can be interesting, but to get the gist of it, it won't be necessary. Now, it's worth noting that linear regression is often used to refer to a slightly more sophisticated model with one additional parameter called bias, weights input plus bias intercepted B. In this model, this mapping function is still in function, but mapping function extension plot looks like a pretty neat origin. Instead of adding this bias parameter B, we can continue to use the model only weights, but another argument X with an extra entry that is always set to 1. So the bias can be quite helpful, and it really improves your predictions. And biases are usually randomized. So let's read through here. The way to correspond to extra entry 1 place of the bias parameter. We frequently use the term linear when referring to affine fractions. Throughout the book, the intercept term bias B is often called the bias parameter of the affine transformation. The distributional general point of view that output of the transformation is based toward being B in absence of any input. The term is different in the statistical bias, in which statistical estimation algorithm expected to the algorithm's expected estimate of a quantity is not equal to the true quantity. Okay. Linear regression is of course an extremely simple and limited algorithm. So now let me actually look up if how is the bias B calculated. So bias is the difference between the uh, true value of the parameter and the model's predictions. That would be the bias. So So bias in a model, we regression does not fit data, part of bias variance, trade-off high bias, okay, cost function. Yeah, so anyways, so that's how bias is calculated. It's just a difference between expected value and then the actual value. And weights would of course be uh, weights is something that happens in neural network. If some weight has performed better, the weights would increase next time. Uh, something like a back propagation. So we will come to these concepts later as we move through this. Coming to frequentist statistics. So this is the second main heading of this chapter. Like I said, first main heading was about the learning algorithms, and yep. So now we are in capacity overfitting and underfitting. So what is the ability to perform well on previously observed inputs is called generalization. So now the generalization and overfitting, underfitting, they all relate to kind of the same concept. And basically, like if your model generalizes well, it means that it is able to perform well even on data that is unobserved. So previously unobserved data, it is able to perform well. And it means that it is not overfit. So the concept of overfit and underfit are not exactly related to this. They're not directly proportional in any way to this concept. They are related. They do affect each other, but the relation is not simple. So now training error is error measured on the training set is called training error. We need to reduce the training error. And what separates machine learning from optimization is that we want a generalization error, also called test error, to be as low as well. Okay, so typically when training machine learning model, we have access to the training set. We can compute some error measure on the training set called as training error. And so far we described is simply an optimization problem. What separates ML from optimization? So optimization is a separate concept. What separates machine learning from optimization is that generalization error, or also called as test error, should be as low as possible, not just the training error, because anyhow you have trained it. So once you have trained it, it should perform well on the tests as well. Like if you're a student, you should actually perform the tests well. It doesn't matter how you perform in the practice sessions. So typically estimate the generalization error of a machine learning model by measuring its performance on a test set as examples that will be collected separately from the training set. In our linear regression example, we trained the model by minimizing the training error. So we actually have test error. Yeah, so again, test error is just x train times weight minus output of the y train. It's kind of similar to the mean squared error. And so the field of statistical learning theory provides some answers. So what exactly, how can we affect performance on the test set when we get to observe only the training set? So statistical learning theory provides some answers. And if the training set and test set are collected arbitrarily, there is a little we can do. If we're allowed to make some assumptions about how the training set and test set are collected, then we can make some progress. So now data generating process, assumptions, independent generalized distribution. So okay, let's come to the concepts of overfitting and underfitting. So underfitting occurs when a model is not able to obtain a sufficiently low error on the training set. So it's not like it will not fit to the training set itself. And overfitting occurs when the gap between training error and the test error is too large, which means it's performing too well on the training set, but very bad on the test set, which means that it is overly attached to the training set, and is performing very poorly on the test set. And underfitting is opposite of that. So I mean, underfitting is not the opposite of that, but it's not even able to fit on the training set. So leave alone the test set. So it's really poorly fit even on the training set. So that would be underfitting. We can control whether a model is more likely to overfit or underfit by altering its capacity. This is a new concept. So you might have heard of underfitting, overfitting, but capacity you probably haven't heard of that much. So informally, a model's capacity is ability to fit the wide variety of functions. Ability to fit a wide variety of functions would be called as model's capacity. And one way to control capacity of learning algorithm is by choosing its hypothesis space. Hypothesis space is just something, just a space of functions, a list of functions where you check will this work or will that work. So going back to the previous paragraph, models with low capacity may struggle to fit the training set. So models with high capacity can overfit them by memorizing the properties of the training set, but overfitting means obviously that they don't perform well on the test set. So high capacity, overfitting, low capacity, so underfitting. So if this is capacity, high capacity means overfit, low capacity means underfit. So how we control capacity of learning algorithm is by choosing its hypothesis space. Set of functions that a learning algorithms is allowed to select as being solution. Now, for example, linear regression algorithm has the set of all linear functions of its inputs as hypothesis space. We can generalize the linear regression to include polynomials rather than just linear functions in this hypothesis space to increase model's capacity. Now, a polynomial degree 1 gives the linear regression model with which we are already familiar, y equals b plus wx or y equals mx plus c in mathematics, pure mathematics. And when introducing a polynomial of a higher degree, x square is another feature provided to the linear regression model. We can improve its capacity, can learn the model that is quadratic as a function of x. Though this model implements a quadratic function of its input, the output is still a linear function of parameters. So we can still use the normal equations to tail the model in closed form. We can continue to add powers of x as additional features. For example, to obtain a polynomial of degree 9, can do this. Machine learning algorithms will generally perform best when their capacity is appropriate for the true complexity of the task. So the capacity needs to be appropriate for the true complexity of the task with the need to perform and the amount of training data they are provided with. Models with insufficient capacity are unable to solve complex tasks. Models with high capacity tend to solve only the training set well. Can solve complex tasks, but their capacity is higher than needed to solve the present task. They may overfit, obviously. So this is the basic concept here. So yeah, so continuing with the thing. So it has been so underfitting, it's lower capacity, overfitting high capacity. This is appropriate capacity. So you don't want it to be too underfit, like it's too weak. I don't want it to be too overly fit either, like it's exactly matching the training set. You want it to be slightly relaxed while being optimal, while being not overly fit, but generalizing well, and having the just right capacity, not high capacity, not low capacity, just the right amount of capacity. Now, capacity is not determined only by the choice of the model. The model specifies the family of functions the learning algorithm can choose from when varying the parameters in order to reduce training objective. This is called representational capacity of the model. So, so far we have described only the way of changing model's capacity by changing the number of input features and simultaneously adding new parameters. There are in fact many ways of changing a model's capacity, and capacity is not determined just by the choice of the model. The model specifies which family of functions the learning algorithm can choose from when varying the parameters in order to reduce the training objective. This is called representational capacity of the model. In many cases, finding the best function with its family is a very difficult optimization problem. In practice, learning algorithm does not actually find the best function, but merely one that significantly reduces the training error. So again, as Elon Musk says, uh, perfection is hard to achieve. You should rather aim on reducing the errors. So minimizing the errors would be a better objective than perfection, because perfection is just unattainable. It can always, the definition of perfection can keep changing always, and you may not quite reach it. And it's not a great heuristic to rely on. So you should always focus on minimizing the errors as much as possible. Now, these additional limitations, such as imperfection of the optimization algorithm, mean that learning algorithms' effective capacity may be less than the representational capacity of the model family. So, effective capacity can be less than representational capacity if, due to these additional limitations, the imperfection of optimization algorithm and others. And modern ideas about improving generalization of machine learning models are refinement of thoughts dating back to philosophers at least early as Ptolemy. Many early scholars may invoke a principle of parsimony that is now most widely known as Occam's razor. Occam's razor. This principle states that among competing hypotheses that explain known observations equally well, one should choose the simplest one. Yeah, well, E equals mc square, and there are two other legendary functions. They're quite simple if you observe them. So it seems that the most groundbreaking formulas or equations tend to be also the most beautiful. So somehow there seems to be a relation between the importance of something and beauty. So the best things are beautiful in some sense. Statistical learning theory provides various means of quantifying model capacity. So the famous one would be Vapnik, Chervonenkis dimension, or a VC dimension. VC dimension measures capacity of a binary classifier. The VC dimension defines as being largest possible value for m for which there are costs of training set and different points of linear operator array. So again, this was only for binary classifier only to measure capacity. And so how they do that actually? So let's go through this. Quantifying the capacity of the model allows statistical learning theory to make quantitative predictions. The most important results in statistical learning theory show that the discrepancy between training error and generalization error is bounded from the above by quantity that grows as the model capacity grows, which shrinks as the number of training examples increases. These bounds provide intellectual justifications that machine learning algorithms can work, but they are rarely used in practice when working with deep learning algorithms. This is in part because the bounds are often quite loose, and in part because it can be quite difficult to determine the capacity of the deep learning algorithms. The problem of determining the capacity of deep learning model is especially difficult because the effective capacity is limited by the capacities of the optimization algorithm, and we have little theoretical understanding of the very general non-convex optimization problems involved in deep learning. Must remember, however, that while the simpler functions are more likely to generalize, you must still choose a sufficiently complex hypothesis to achieve low training error. Typically, training error decreases until the asymptotes to minimum possible error was value as model capacity increases. Typically, generalization error has a U-shaped curve as a function of model capacity. This is illustrated in the figure next page. So as you can see, training error generation. Now, this particular diagram has been was showed in a video by Welsh Lab, something like that, on YouTube. So he tries to explain why the training error decreases with the more you train, but generalization error always keeps increasing. Now, there's a so which means that the more you train on your data, you obviously are overfitting here. Okay, this is obviously an overfitting because you have trained too much on the data. This is underfitting because you haven't trained anything on your data. So this is overfitting, underfitting only in with reference to the training error, obviously. And so when your model is overfit, obviously it will perform poorly on a test set or any other like or random data points, and and underfitting also it perform very poorly. Now there's a concept called a double descent, which means that this curve, as you keep on training it, the error seems to decrease again. So that's why it's called double descent. So it's a concept, you can look it up. So this was discovered in 2017 or 2019, somewhere around that. So turns out the more you train, you can actually come up with the lower training error. So double descent idea that would be. So let's go back to the textbook stuff here. Parametric models can learn a function described by a parameter vector whose size is finite and fixed before any data is observed. Non-parametric models have no such limitation. So parametric models can learn a function described by a parameter vector size is finite and fixed. So non-parametric would be the opposite. Now, unlike linear regression, which has fixed length of weights, the nearest neighbor regression model simply stores x and y from the training set. When asked to classify a text point text, the model looks up the nearest entry in the training set and returns the associated regression target. In other words, y equals phi I, where I equals arg min xi minus x of L2 norm square. So that's one concept. Base error is something. So let's say when they are incurred by an oracle making predictions from the true distribution is called Bayes error. So yeah, this will come under like probability statistics. So let's go to the no freelance theorem. So no freelance theorem, I think we did go through this concept in the previous chapters. It says that there's no one thing that is useful in all cases. So in so yeah, let's read this thing actually. Averaged over all possible data generating distributions, every classification algorithm has the same error rate when classifying previously unobserved points. In other words, no machine learning algorithm is universally any better than any other. So there's no freelance, guys. Okay, basically, there's no one thing that useful for all cases. So this means that goal of machine learning research is not to seek a universal learning algorithm or the absolute best learning algorithm. Instead, our goal is to understand what kinds of distributions are relevant to the real world that an AI agent experiences. What kinds of distribution are relevant to the real world AI experiences. So, and what kinds of machine learning algorithms perform well on the data driven from the kinds of data engineering distributions we care about. So, no general rule, no free lunch. It all depends on the context. Again, unless it's LLM, isn't it? So, as of 2025, this book was obviously written in 2019. But if you guys see in the 2025, we obviously have LLM, which can be used in all cases, it might seem. But then again, this only applies to machine learning algorithms, and LLM is quite too big to be called just a simple algorithm. Nonetheless, LLMs aren't yet so good that they are universally applicable in every case. I'm sure there's areas where it's not applicable. So let's go to regularization. So the no free runs theorem implies that we must design our machine learning algorithm to perform well on a specific tasks. Obviously, we do so by building a set of preferences into the learning algorithm. With this preference aligned with the when these preferences align with the learning problems we ask the problems algorithm to solve, it performs better. So weight decay is something you add to, let's say, the cost function here. For example, we can modify trading criterion for linear regression to include weight decay. To perform linear regression with weight decay, we minimize the sum of comprising both mean squared error on the training set and criterion J. So JW is J of W is the criterion. It expresses preference for weights to have smaller squared L2 norm. So MSC squared on the trained data set plus lambda weights transpose times weights, where lambda is a value chosen ahead of time that controls the strength of our preference for smaller weights. If lambda equals 0, we impose no preference, and large lambda forces the weights to become smaller. Minimizing the criterion JW results in choice of weights that make a trade-off between fitting the training data and becoming small. Training data and becoming small. This gives us solutions that have smaller slope, but put weight on fewer features as an example of how we can control the model's tendency over fit and underfit. By weight decay, we can have a high degree polynomial regression model with different values of lambda. Underfitting, excess lambda. Medium lambda, it's appropriate weight decay. Overfitting, lambda is 0. So again, too much lambda. So we don't have to have too much lambda. So we don't fit in that case. So this is exactly, so lambda seems to be exactly opposite to capacity. And let's just write data set. And so let's just pause here and I'll be back soon. Yeah, so I just took a mental break. Let's continue with our stuff. Regularization is any modification we make to a learning algorithm that is intended to reduce its generalization error, but not its training error. So need to reduce the generalization error, but not the training error. Because if you reduce the training error, you're obviously going to underfit. So it's a perfect balance that you need to strike, which is called regularization. So regularization along with the optimization of central concerns of the field of machine learning. Okay, rival its importance only by optimization. So regularization, optimization, two big things. Just remember that. So no best form of regularization is present. Instead, we must choose from a regularization that is well suited to the particular task at hand. So no freelance theorem applies here as well. Now, need to remember that regularizer controls weight decay. Weight decay in turn controls overfitting or underfitting. Regularization directly doesn't control overfitting or underfitting. So regularizer controls weight decay controls overfitting or underfitting. So now the second main thing that we learned was capacity overfitting and underfitting. First was learning algorithms, capacity overfitting and underfitting. Now we come to hyperparameters and validation sets. Hyperparameters are just parameters that are that you control to, to affect the behavior of the learning algorithm. So to reiterate, most machine learning algorithms have several settings that we can use to control the behavior of the learning algorithm. So control the behavior of the learning algorithm. There are several settings. These are called hyperparameters. So these are not baked into the uh, algorithm. So like there is no, while training, these parameters are not something that are inferred from the data or something or anything. These are something that you put in from the outside. It's called hyper. Hyper means from the outside you are affecting these parameters, and values of hyperparameters are not adapted by learning algorithm, like I said. And though we can design a nested learning procedure where one learning algorithm learns the best hyperparameters for another learning algorithm, that's also we can do it. But in general, this is not something that is present in the data itself. In the polynomial regression example we saw in figure 1.2, single hyperparameter is present, the degree of polynomial which acts as capacity hyperparameter, and the lambda value to use the control strength of the vertical and other using parameter. So yeah, capacity and lambda value are two examples in the previous uh, example that we saw. These are two hyperparameters there. Sometimes a setting is chosen to be a hyperparameter that learning algorithm does not learn because it is difficult to optimize. More frequently, setting must be hyperparameter because it is not appropriate to learn that hyperparameter in the training set. This applies to all hyperparameters that control model capacity. So you need a validation set to solve that. And so we earlier discussed a wild out test composed of examples from the same distribution that the training set can be used to estimate the relation of learner. So we do that, and yeah, so this is a general thing that we use 80% of training data for training, 18% of the, and the rest 20% for validation. So there's usually like three sets, um, which is not explained here anyways. So we use 50% of training data for training and 20% for validation. And there's also another test set which is different from the training set. So this is again like, this is let's say training set, this is test set. Within the training set itself there is like this part would be 80%, 20%, let's say, to be for actual training. This would be for validation. So coming to cross validation, dividing data set into fixed training set and fixed test set can be problematic. The results in the test set are small. Small test set implies statistical uncertainty around the estimated average test error, making it difficult to claim that algorithm was better than algorithm B in given tasks. So when data set has hundreds of thousands of examples or more, this is not a serious issue. When the data set is too small, you need to use cross validation. So repeat. So basically, you repeat training and testing completion on different randomly chosen subsets, so splits to original data sets. That's why it's cross validation. So you don't always take the same training and test set or training and validation set. So every time you take a different training and test set, different validation set. This is especially for small data sets. Now coming to the fourth major heading of this chapter, which would be estimators, bias, and variance. So what is an estimator really? So function estimation is really just same as estimating parameter theta. The function estimator f is simply a point estimator in function space. So they first went through the point estimator. We'll just estimate sort of points. Let x1 dot xm be a set of m independent and identically distributed data points. A point estimator is any function of the data theta m equals g of x1 dot xm. Okay. Point estimation is attempt to provide best single best prediction of some quantity of interest. Best prediction. In general, the quantity of interest can be a single parameter or the vector of parameters in some parametric model, such as weights in our integration example. Function estimation is just same as estimating parameter theta, except the function estimator is simply a point estimator in function space. Bias of an estimator is defined as bias of theta of m equals expectation of the theta of m minus theta value. So estimator bias. So the given example. Now to make variance and standard error. Variance, I hope you guys know what variance means. Standard error of mean is given by standard error of mean equals variance, the square root of variance of 1 over m sum of x points from 1 to m basically the standard deviation divided by square root of m, where m is the size of the data set. Now, in machine learning experiments, it is common to say that algorithm A is better than algorithm B if the upper bound of the 95% of confidence interval for the error of algorithm A is less than the lower bound of the 95% confidence interval for the error of algorithm B. So this is one more thing you need to guys remember. So it's kind of a basic concept, really. Basic A is just better than B, and that's how you choose A. Now, trade-off of bias and variance. So this is another important concept: trading of bias and variance to minimize the mean squared error. So bias measures the expected deviation from the true value of the functional parameter. Variance, on the other hand, provides a measure of the deviation. Yeah, bias is the just expected deviation. Variance is the measure of deviation, expected variable. Now, this variance, there is a difference between the bias and variance, and you need to really balance the trade-off. So what happens when we are given a choice between two estimators, one with more bias and one with more variance? How do we choose between them? So for example, imagine that we interested in approximating function shown in figure 5.2. We are offered choice between a model with large bias or large variance. How to choose between them? So the trade-off, this is how calculated. So is to use cross-validation. Empirically, cross-validation is highly successful on many real-world tasks. Alternatively, we can use also compare the mean squared error of the estimates. So mean squared error will be basically bias of theta m squared plus variance of theta m. Now, when in confusion of bias and variance, use cross-validation or MSE. The same thing, and both of which are estimators. The MSE measures overall expected deviation in squared error sense between the estimator and the true value of the parameter theta. It is clear from the equation 5.54. Where writing MSE incorporates both bias and variance. Desirable estimators are those with small MSE, and these are estimators that manage to keep both their bias and variance somewhat in check. So as you can see, so this graph explains it really well. So general trend is that so there's an underfitting zone, there's overfitting zone, there is optimal capacity is just here, and as you can see, the training error is decreasing as the train keep on training. Generalization error keeps decreasing and then increasing because there's overfitting happening here. So optimal capacity is just here. And we also have bias and so okay, so this is not training error and the thing error. So this is actually bias and variance. So bias decreases as variance increases. And generalization error also increases as variance increases. So yeah, so increasing capacity tends to increase variance. As you can see, as capacity increases, variance is also increasing, but bias decreases. So the reason is because the more you train the bias, which is kind of like MSE, keeps decreasing. Variance, the measure of deviation increases because there is overfitting happening. It's high capacity, so there's high variance. Now, next topic is consistency. And, let's go what that is. So I wrote this as a beautiful equation. Let's see exactly why. So far, we discussed properties of various estimators for a training set of fixed size. Usually, we are also concerned with the behavior of estimators as the amount of training data grows. Behavior of estimator amount of training data. Particularly, we usually wish that as the number of data points m in a data set increases, our point estimators converge to the true value of the corresponding parameters. More formally, we would like that limit p limit as m tends to infinity of theta m would be equal to theta. So it's kind of a beautiful equation. So let's see exactly why. The symbol p lim indicates convergence in probability, meaning that for any epsilon greater than 0, probability of theta m minus theta is greater than epsilon tends to 0 as m tends to infinity. So the condition described by equation 5.55 is known as consistency. This is basically consistency. Also referred to as weak consistency, with strong consistency referred to as almost sure convergence of theta to theta. Almost sure convergence of a sequence of random variables x1, x2, to value x occurs when probability of limit of m tending to infinity of x of m equals x equals 1. So consistency, so here the bias induced by the estimator diminishes as the number of data example grows. As we saw, bias does decrease as data grows. That's what consistency ensures. However, the reverse is not true. If the consistency, if number of data decreases, bias does not decrease. Asymptotic unbiasedness does not imply consistency. So consistency means there is bias induced decreases as data increases, but asymptotic unbiasedness does not mean consistency. So, for example, considering estimating the mean parameter of a normal distributor that consisting of m samples, try to say converse estimator. In that case, the estimator estimator is asymptotically biased. So this is not consistent estimator, not case that basically consistency means that the bias induced by the estimator diminishes as the number of data example grows. Bias as number of example grows. The reverse is now true. Asymptotic unbiasedness. So zero biasedness, asymptotic means like it's going like this. Does not mean consistency. Okay. As an example, I would really like you to study this part. Consider estimating the mean parameter mu of an anomaly distribution n, the dataset consisting of m samples. We could use the first example x of the dataset of an unbiased estimator theta equals x1. In that case, estimation equals theta. So the estimator is unbiased no matter how many times the data points are seen. So of course implies that the estimator is asymptotically unbiased. However, this is not a consistent estimator because it's not the case that theta m tends to theta as m tends to infinity. Yeah, so unbiasedness doesn't imply consistency. Consistency ensures that bias induced by estimator diminishes as the number of data example grows. Unbiasedness does not imply consistency. So the next concept would be, it may look like MSE, mean squared error, but it's really not that. It's maximum likelihood estimation. So what is maximum likelihood estimation? We'd like to have some principle from which we can derive specific functions that are good estimators for different models. So we are choosing principle from which we can derive specific functions that are good estimators for different models. So for choosing a good estimator for different models, we are having some principles. So these principles is for choosing the right functions, which are good estimators in turn. So MLA helps finding good estimators, which in turn helps choose the actual ML prediction or estimation. So ML does not help with the actual ML prediction. And minimum maximum likelihood estimation, as the term itself says. So what estimation is maximally likely to be good? So that's what we are trying to do here. Now, minimizing the KL divergence corresponds exactly to minimizing the cross entropy between the distributions. As we have seen, KL is Kullback-Leibler divergence. Many authors use the term cross entropy to identify specifically the negative log likelihood of a Bernoulli softmax distribution, but that is the misnomer, as the loss consisting of a negative log likelihood is a cross entropy between the empirical distribution defined by the training set and the probability distribution defined by the model. For example, mean squared error is the cross entropy between empirical distribution and Gaussian model. Well, there's that. Now, conditional log likelihood and mean squared error. Let's look at that. The maximum likelihood estimator can readily be generalized to the case where our goal is to estimate a conditional probability P of y such that x theta in order to predict y given x. This is actually the most common distribution because it forms the basis for most supervised learning. MSE is a maximum likelihood estimation procedure. As we have seen, maximum likelihood estimator has several desirable properties. So what are those properties exactly? The true distribution P data must be live in the conditions of, so these are the conditions. So under proper conditions, maximum likelihood estimator has the property of consistency. Okay. Meaning that as the number of training example approaches infinity, maximum likelihood estimation of a parameter converges to the true value of the parameter. And the conditions are basically true distribution P data must lie within the model family P model. Otherwise, the no estimator can require P data. The true distribution P data must correspond to exactly one value of theta. Otherwise, maximum likelihood can recover the P data. Correct P data, but will not be able to determine which value of theta was used by training generating processing. So there are other inductive principles besides maximum likelihood estimation, many of which have the property of being consistent estimators. However, consistent estimators can differ in their statistic efficiency, meaning that one consistent estimator may obtain lower generalization error for a fixed number of samples n, or equivalency may require fewer examples to obtain a fixed level of generalization error. Statistical efficiency is typically studied in parametric case. So again, no consistent estimator has a lower mean squared error than the maximum likelihood estimator. So no consistent estimator has a lower mean squared error than maximum likelihood estimator. So maximum likelihood estimator always has the lowest mean squared error than any consistent estimator. Okay. For these reasons, consistency and efficiency, maximum likelihood is often considered to be the preferred estimator to use for machine learning. And when the number of examples is small enough to yield overfitting behavior, regularization strategies such as weight decay may be used to obtain a biased version of maximum likelihood that has less variance when training the data is limited. When training data is limited. So coming to the next main heading, Bayesian statistics. So this is a hell of a thing. It's a very interesting stuff. And we shall go to it. So Bayesian statistics, Bayesian probability, invented by Bayes. Don't remember the full name of the person. Pretty sure he was European. So far we discussed frequentist statistics and approaches based on estimation of single value of theta, but making all the predictions thereafter based on that one estimate. Another approach is to consider all possible values of theta when making a prediction. This latter domain is the domain of Bayesian statistics. So using all maximum likelihood estimator is the best estimator. So just remember that. So now related to maximum likelihood estimation, Bayesian estimation offers two important differences. Unlike maximum likelihood approach that makes predictors using a point estimation of theta, Bayesian approach is to make predictions using a full distribution over theta. So again, we're considering the probability distribution. This is Bayesian statistics. Obviously, we're going to use probability here. And unlike maximum likelihood, which is like a point estimator, we're using full distribution here in Bayesian statistics. I'll give an example. Could be interesting. So this whole book is actually open source. So you mean you can access the entire book for free online, and you could print it as well if you have a printer of sorts. And all of this can be easily accessed very quickly legally by the authors themselves. They have published the entire book for free. So you can just search deep learning, Aaron Goodfellow et al. Or something. You will get the book. And next topic is maximum a posteriori estimation. So a posteriori and a priori, there are some English words that are kind of interesting. A priori and a posteriori. A priori is something that happens like when you already know about it. So let me do a quick search about it. So a priori knowledge is independent of experience. So derived from reason and logic alone. A posteriori knowledge is based on empirical evidence and experience. So let's write it down. A priori is something from logic. Okay, from logic. So a priori knowledge. Knowledge. Posteriori is something that empirical knowledge. So knowledge derived from empirical evidence. So posteriori. So why exactly called? Because a priori means from what comes before. Okay, from what comes before. A posteriori means from what comes after. Okay, so logic comes always before. So prior. So logic always comes before. Okay, before. Prior means before, and posteriori means after. So here obviously logic comes before everything. So you're deriving it from the axioms. A posteriori means something that comes after because there has been some evidence here. So maximum a posteriori estimation. So a posteriori means like this says there's been some empirical evidence, and the maximum of a, a posteriori estimation map estimation. So while the most principled approaches make predictions using the full Bayesian posterior distribution over the parameter theta, it is still often desirable to have a single point estimate. So the Bayesian does a full distribution estimation. So they're saying that it is still often desirable to have a point estimation. One common reason for designing a point estimation is that most operations involve Bayesian posterior for most interesting models are interactable. So obviously the full things are hard. Obviously, full computation is hard and intractable. And point estimation offers tractable approximation. So tractable means it's possible. It's easy to do it, easier to do it. One rational way to do it is to choose maximum posterior point estimate, and that's exactly what that is. Map Bayesian inference provides a straightforward way to design complicated yet interpretable regularization terms. For example, a more complicated penalty term can be derived by using a mixture of Gaussians rather than a single Gaussian distribution as the prior. Going to the next main heading, supervised learning algorithms, and as you might know, here the algorithms have been trained on a similar data set upon which they are being tested. And coming to the first heading, probabilistic supervised learning. The process is known as logistic regression. Somewhat strange name since we use the model classification rather than regression. Remember that whenever they say linear regression, this so it is meant for regression, but logistic regression is something that used for classification rather than regression. So we're not just doing the next number prediction based on prior stuff, we're classifying it based on prior knowledge. So the first classification algorithm that I have mentioned here. So the next topic mentioned here is support vector machines, SVMs. Unlike logistic regression, the support vector machines does not provide probabilities, but only output is a class identity. Outputs a class identity. So vector machines, it uses one hot encoding, I suppose, and there is a kernel trick. So let's actually go through this. Wait, let's do valve and vet. SVM predicts the positive class is present when weights transposed times x plus b is positive. Likewise, predicts the negative class present when this thing is negative. One key innovation here is the kernel trick. Kernel trick consists of observing that many machine learning algorithms can be written exclusively in terms of dot products. In examples. Okay. Example, it can be shown that the linear function used by support vector machines can be rewritten as wx plus p equals p plus alpha x transpose x. Okay. So after replacing dot products with kernel revelations, we can use predictions of it. So just remember that SVMs use this kernel trick, and kernel trick is a mathematical concept, which the scope of which is out of this book, as they themselves are saying here. The function is non-linear with respect to x. The relationship between phi x and f of x is linear, and also the relationship between phi and f of x is linear. The kernel-based function is easily equivalent to preprocessing data by applying phi x to all inputs. The linear model is the new transform space. Okay, the kernel trick is powerful for two reasons. One, first, it allows us to learn models that are non-linear as a function of x using convex optimization techniques that are guaranteed to converge efficiently. So, kernel trick efficient for two reasons. One is that it allows us to learn models which are non-linear as function of x, like circle or something like that, using convex optimization techniques. Okay, using convex optimization techniques that are guaranteed to converge efficiently. So guaranteed to converge efficiently. This is possible because we consider phi fixed and optimized only alpha. That is, the optimization algorithm can view the decision function as being linear in a different space. Second, the kernel function k often admits an implementation that is significantly more computationally efficient than naively constructing two phi x vectors and explicitly taking the dot product. Again, second, the kernel function k often admits an implementation that is significantly more computationally efficient. So it's basically computationally efficient and naively constructing two phi x vectors. So it not only does it allow you to calculate learn models that are nonlinear. Not only does it allow you to learn the models that are nonlinear using convex optimization methods and guaranteed convergence, which helps you to learn basically. But it also is computationally efficient. That's why I use the kernel trick, and SVMs use that. And so in some cases, phi x can even be infinitely dimensional. And so what exactly is phi x that they're talking about here? Let's see that learning predicts feature function phi x. Okay, yeah. So we did write all the notations here. Let's see if we have them. No, there's no. So phi x is basically sorry, it's called phi x is basically a feature function. In some cases, phi x can be can even be infinite dimensional, in which would result in infinite combination cost for the naive explicit approach. In many cases, k x dash is non-linear tractable function of x, even if phi is intractable. Most commonly used kernel is Gaussian kernel. Gaussian kernel is kernel tricks, which has these two features: combination efficient, and it can also train on non-linear models using convex optimization method. And so standard normal density is kernel inverse radial basis function. Radial basis function, again, like I said, if you search this concept for kernel trick and Gaussian kernels, radial basis function, you will get graphs something like a circle form. And this kernel trick really helps you to train a model on these nonlinear functions. And so Gaussian kernel, we can think of Gaussian kernel as performing kind of a template matching and training example with the template matching and then level kernel machines and kernel methods. The major drawback to kernel machines is that the cost of evaluating the decision function is a linear number of training examples. Like example constitutes term, decision functions for indicate this learning requires known support vectors. These training examples are known as support vectors. The current deep learning renaissance began when Hinton et al., Jeffrey Hinton, godfather of AI, demonstrated that a neural network could outperform the RBF kernel SVM on the MNIST network benchmark. So MNIST is the famous dataset. You can look it up. You might have came across it already. So again, this is a like a breakthrough moment here. Might as well like mark it something like current deep learning renaissance began when Geoffrey Hinton et al. And his team. Geoffrey Hinton, who is now called as Godfather of AI and the recipient of Nobel Prize and other computer prizes, uh, demonstrated in 2006 that a neural network. So again, this 2006 is the benchmark date that a neural network could outperform a RBF kernel support vector machine on the MNIST benchmark radial basis function kernel. Radial basis function kernel is based on Gaussian kernel, which is kernel tricks. The neural networks outperform this radial basis function using which uses the support vector machines on the dataset MNIST. So going to the next part, other simple supervised learning algorithms, k-nearest neighbors and a family of techniques that can be used for classification or regression. Again, the k-nearest is one of the most popular classification techniques, the most simplest ones as a non-parametric learning algorithm. K-nearest will be not restricted to a fixed number of parameters. So yeah, there's quite some explanation going here. So STM could be in any dimension, hence the word hyperparameter. Not really. So support vectors SVM could be in any dimensions, hence the word hyperplane and not 2D plane. Hyperplane means a plane one dimension less than its ambient space. Hyperplane basically one dimension, a plane that is one dimension less than ambient space. So example, 2D plane is hyperplane in a 3D ambient space. Support vector machine is a supervised margin models with associated learning algorithms that analyze data for classification and regression analysis. Called support vectors cause the data point closest to the decision boundary, it's called hyperplane, are the ones that support or define the position and orientation of this boundary. So support vector machines, because support vectors because the data points closest to the hyperplane decision boundary, also called as data points closest to the hyperplane, are the ones that support or define the position or orientation of the boundary. So points closest to the hyperplane, the margin. Okay, this is the hyperplane and this is the margin. Points closest to this hyperplane or the margin or the decision boundary are the ones that define the position and orientation of that boundary. So that's the concept here. So decision tree is another famous one concept, which is used for classification. You see, nearest neighbor predictors and decision trees have many limitations, so that's why we don't use them in the complicated stuff. And it's also not really fleshed out here. So this is like a decision tree, and see how it works. You go here, you go here, you go here. Like the top one is different diagram than the bottom one. The tree divides into regions. The top one is divided like an actual tree. So this is more efficient way to describe it, I guess, and this can take much space. Now, if we have learned about supervised learning algorithms, let's go to the unsupervised learning algorithms. The distinction between supervised and unsupervised is not formally and rigidly defined exactly because there is no objective test for distinguishing whether value is a feature or a target provided by the supervisor. So it's kind of a gray area. What is supervised? What is unsupervised? Can be quite confusing. And, the reason is they're saying there's no objective test for distinguishing whether a value is a feature or a target provided by the supervisor. So, I mean, let's say that there's a set of data here. Which one is exactly a feature, which is a target? You cannot say it. So supervised and unsupervised algorithms are not exactly that much different after all, because if I'm going to train this entire book, what is the feature and what is the target here? So there is no feature, there is no target, and that's why most LLMs are undergo unsupervised training. Reinforcement to supervised fine tuning is only done at the end when the model is converted to like an instruct model. So classic unsupervised learning task is to find the best representation of the data. The best can mean different things, but generally speaking, they're looking for representation that preserves as much information about X as possible while obeying some penalty or constraint aimed at keeping the representation simpler and more accessible than X itself. So there are multiple ways of defining a simpler representation. Uh, yeah, so what are the so a classic unsupervised learning task is to find the best representation of the data. Okay. For example, I take this book. So what is the best representation so that I can actually train my model on it? Okay. Remember again that all these come under the idea that these are representation learning concepts. Okay. So they're all representation learning that is happening. Okay. So in an unsupervised thing, you're going to try to learn the representation of the data. The best we can mean different things. So what's exactly the best representation here? Best can mean many things. So basically, we're looking for a representation that preserves as much information as possible while obeying some penalty or constraint aimed at keeping the representation simpler and more accessible than X itself. Okay, now how do we define much information? Okay, before that, let's ask how do you define simpler? Maybe that covers also the stuff on what is more information. Three of most common include lower dimensional representations, uh, sparse representations, independent representations. Okay, low dimensional representations attempt to compress as much information about X as possible to a small representation. Okay, this is lowering the dimensions. Sparse representations tend to make the data so big that the data is sparse. So embed the data set into a representation whose entries are mostly zeros for most inputs. Again, a sparse matrix, let's say. The use of sparse representation typically requires use of dimensionality of the representation so that the representation becomes mostly zeros and does not discard too much information. This results in an overall structure of the representation that tends to distribute the data and the access of the representation space. Yeah, now, what about the independent representations? Attempt to disentangle the sources of variation underlying the data distribution such that the dimensions of the representation are statistically independent. So basically trying to disentangle the sources of variation underlying the data distribution. So trying to decrease the variation here. Okay, so as you can see, there's much variation, little variation. So there's three types where the simpler representation can be found, basically by lowering the dimensions, by making this representation sparse, or by just reducing the variance of the statistical data, which by disentangling the thing. So the notion of representation is one of the central themes of deep learning. Like I said, so as you can see, deep learning, the whole concept of deep learning is part of representation learning, which is a part of machine learning, which is a part of AI. So most people will show you the AI has machine learning in it and machine learning has deep learning in it, and they don't show the representation learning much. So representation learning is quite important. Okay, so as you can see here, um, in unsupervised learning, you learn to learn the representations here. Okay, you learn the representations. What's principal component analysis? Another tasty concept here. So uh, basically, it's I think we have went through this topic earlier. So PCA is basically a method to compress data. Okay, so okay, let's go through this. So here, yeah, so we did see go through it already in 2.12 section. Principal component analysis algorithm provides a measure of compressing data. We can also view PCA as unsupervised learning algorithm. Yeah, so we can also view PCA as unsupervised learning algorithm as well. So this representation is based on the two of the criteria for the simple representation described above. PCA learns the presentation with lower dimensionality than the original input, and it also learns the presentation whose elements have no linear correlation with each other. So this is the first step towards criterion of learning representations whose elements are statistically independent. So statistical independence. To achieve full independence, a representation learning algorithm must also remove the non-linear relationships between the variables. So PCA learns orthogonal linear transformation of the data that projects on and protects the representation of Z prevalence of figure this one. So that we can learn a one-dimensional representation with connect to original data. So going to the math behind the PCA. So there's eigenvectors and on. So here we exploit an alternative derivation of the principal components. The principal components may also be obtained by a singular value decomposition, also called as SVD. And yes, so you do it. Let's go to the next part here. This ability of PCA to transform data into representation where the elements are mutually uncorrelated is a very important property of PCA. It's a simple example of representation that attempts to disentangle the unknown factors of variation under the data, making it statistically independent and mutually uncorrelated. So mutually uncorrelated because training the data into something like this, representation like this. While correlation is important category of dependency between the elements of the data, we're also interested in learning representation to disentangle more complicated forms of feature dependencies. For this, we need more than what can be done with a simple linear transformation. So let's go to K means clustering. Uh, yeah, so basically clustering algorithm divides certain data into K different clusters. Examples that are not near each other. Just think of algorithm as providing a k-dimensional one-hot code vector h representing an input x. Clustering problems is problem is inherently ill-posed in the sense that there is no single criterion that measures how well a clustering data is possible in the real world. Exactly. So how do you cluster things or group things anyway? For example, if there is red vehicles and a cluster of gray vehicles, would you classify the vehicles into cars and trucks, or would you classify them based on the color? So this is a ill-posed problem in itself. It's the clustering is useless. It's not it's ill-posed inherently. So uh, that illustrates the example that we prefer a distributed representation to one hot code representation. That's why one hot encoding is much worse. So we want something that is much more distributed. So having many attributes reduces the burden on the algorithm to guess which single attribute we care about. So this is where the things like CNN enter. So like something like convolutional neural networks and all, they learn many features of the image. They don't just learn like one or two features. And this is why deep learning is also helpful. Deep learning does exactly this. Deep learning helps to learn the representations, which are much more complex. So they learn many representations of the data instead of just like one hot encoding, like something like k-means clustering, which is very simple. And our real world is not that simple, obviously. Our real world is much more complicated, and you cannot just classify vehicles into red or white vehicles when they can also be classified much better into cars, trucks, and buses. So the next big concept here is the stochastic gradient descent, just the extension of the gradient descent. Um, so what's exactly stochastic gradient descent? Gradient descent uses the entire data set to compute the gradient. and update parameters, letting a slow but smooth convergence. Now, stochastic gradient descent updates parameters after each individual data point, making it faster and more scalable, but with noisy oscillating convergence path. So let's get on here. So normal GD is full data to compute gradient and update params. So slow, smooth convergence, whereas SGD uses uh, updates parameters after each individual data point, making it faster, scalable, but noisy, oscillating convergence. So gradient descent would be smooth. Let's say we are like this. Gradient descent would be smooth. Let's see data like this. Stochastic would be like this. Okay. So GD, GD, GD is GD, stochastic gradient descent. This full data, this is full data. Only after going to full data does it start to slowly, smoothly converge. And stochastic gradient descent is each individual point and updates parameters after each individual point. It's faster, scalable, much better, but it's noisy and convergence can be oscillating and erratic. So it finds the low value of the cost function quickly enough to be useful. So again, the symbolic notations of running time are like big omega fan of the lower bound, theta n upper and lower bounds, O big O of n, just upper bound. So big O of n that we always talk about is just upper bound. Big theta of n is upper and lower bound. Omega of n is the only lower bound. Only lower bound, big omega of n. Only upper bound, big O of n. Theta n, upper and lower bounds. One can argue that the symptotic cost of training a model with SGD is big O of 1 as a function of m. In academia studying in 2006, deep learning was initially interested in me because it was able to generalize to new examples better than competing algorithms in trained and medium-sized datasets to thousands of examples. Soon after, deep learning generalized garnered additional interest in industry because it provided a scalable way of training nonlinear models in large datasets. Coming to building a machine learning algorithm. Okay, so just went to SGD here and we went to the difference between GD and SGD. Building a machine learning algorithm, combining specification of dataset, cost function. So yeah, all the deep learning algorithms can be described as a particular instances of a fairly simple recipe. Okay, combining a specification of dataset, cost function, an optimization procedure, and a model. For example, linear regression algorithm combine dataset consisting of a model specification P model y of x equals n of yx transpose w plus b comma 1. And in most cases, the optimization algorithm defined by solving whether the gradient of the cost is zero is in the normal equations. And cost function, negative log likelihood is so that minimizing cost function because maximum likelihood estimation. So the recipe for constructing a learning algorithm by combining models, costs, and optimization algorithm supports both supervised and unsupervised learning. So basically, you can mix and match. Yeah. So what were the challenges with which motivated deep learning? Why was traditional ML not enough? As we saw already, data is much more complex than just white or black or categorical. It's not just regression won't help. Let's see some other reasons why. Because there are challenges with working with high dimensional data and how the mechanisms used to achieve generalization in traditional machine learning are insufficient to learn complicated functions in high dimensional spaces. such as the spaces, also often impose high computational costs. So you could possibly, maybe you could design an AI with just basic ML models, but perhaps it would be so difficult that either it would probably require infinite computation, like almost too much computational resources. So that's where deep learning comes. Deep learning is much smarter, it's much more efficient, it learns the data better, and it's faster. So one of the big challenges here is the curse of dimensionality. So yeah, so the kernel trick. Let's go to like a brief interlude of kernels. What's exactly kernel trick? Example SVMs. Functions that enable algorithms to operate on higher dimensional space without explicitly computing the transformation. Those are kernels. Example kernel trick. So that enable algorithms. So the kernel tricks are those kernel functions that enable algorithms to operate on higher dimensional space without explicitly computing the transformation. So without even computing the transformation, and as we saw, kernel trick does help with computation. I mean, you don't have to compute everything there. So uh, as we saw, it's computationally efficient. Kernel tricks are, and also especially non-linear models. So, so talking about the curse of dimensionality, many ML models, ML problems have become extremely difficult when number of dimensions the data is high. This phenomenon because of dimensionality, whereas concerned the number of possible distinct combinations of variables increase exponentially as the number of variables increases. So, curse of dimensionality there are many places in computer science, especially in machine learning. Challenge is basically, I mean, there's just too much data, too many dimensions. It would be crazy to uh, how do you configure them? So what meaning for many traditional machine learning algorithms is simply assume that the output at a new point should be approximately same as the output at the nearest training point. Use a number of examples and start training examples without any possible circumstance. So second would be local consistency and smoothness regularization. So what's that? So we may also discuss the prior beliefs as directly influencing function itself and only indirectly acting on parameters prior the effect on the function. So prior beliefs is directly influencing the function itself and then directly acting on parameters via effect on function. Additionally, we normally discuss prior beliefs as being expressed implicitly by choosing algorithm best toward using some class of function over another even by the small of tests in terms of probability distribution representation of degree of belief functions. Among the most widely used of these implicit priors is the smoothness prior or local consistency prior. Prior states that the function we learn should not change very much within a small region. So in a small region, function that you learn should not change much within that region, should be good. It's the local constancy problem. And throughout this book, we'll describe how deep learning introduces additional explicit and implicit priors in order to reduce generalization errors on sophisticated tasks. If you know a good, simple answer for an input x, then the answer is probably good in the neighborhood of x. If you find, I mean, simple as that. I mean, this is so obvious. If you find a good answer for an input x, probably that same answer would be good in that area of x. It's called local constancy prior. If we have several good answers in some good neighborhood, we will combine them by some form of averaging and interpolation to produce an answer that agrees with as many of them as much as possible. So that's what this says. Like function we learn should not change very much within a small region. That's what it says. Local kernel can be thought of as similarity function that performs template matching by measuring how closely a test example resembles training example xi. Much of the modern motivation for deep learning is derived from studying the limitations of local template matching and how deep models are able to succeed in cases where local template matching just fails. So the last concept here is manifold learning, and manifold is just a connected region. So call it manifest, manifold. So machine learning problems seem hopeless if we expect the machine learning algorithms to learn functions with interesting variations across all of real number set. Manifold learning algorithms surmount this obstacle by assuming that most of real numbers consist of invalid inputs. Then interesting inputs only occur along collection of manifolds. So this is a kind of a belief or axiom in that this algorithm purports. Uh, so basically, you're putting constraints. So basically, any big problem, if you want to any big problem, you want to reduce it. If you want to solve it, you want to put some constraints in it and make it simpler. So that's what manifold learning does by assuming something, which is that most of real numbers consist of invalid inputs, and the interesting inputs occur only along a collection of some manifold, obtaining small subset of points. The interesting variations in the output of the learn function occurring only along the directions that lie on the manifold, like this. It kind of believes that the interesting numbers occur only along the certain manifold lines. Move from one manifold to another. Manifold learning, when it is in the case of continuous supervised setting, all these probability concentration has generalized but first observation in favor of manifold hypothesis is that probability distribution over images, text strings, and sounds that occur in real life is highly concentrated. So they did see some proof in favor of this hypothesis. Then they saw images, text strings, sounds. They seem to have some concentrated and they seem to have some relation there. Second argument in favor of manifold hypothesis is that we can also imagine such neighborhoods and transformations, at least informally. In the case of images, we can certainly think of many possible transformations that allow us to trace out a manifold image space. We can gradually dim or brighten the lights, gradually moving or rotating objects in the image. As you can see, when you try to increase the exposure or decrease the exposure or move objects in the image, they tend to move along some particular region, also called as manifold. Gradually add the colors to the surface of the objects, etc. So this is the second argument in favor of manifold hypothesis, and the first argument in favor of manifold hypothesis. So the data of all these images, text, sounds occurred along some similar pattern like a manifold. By the end of the book, we will have developed the method necessary to learn such a manifold structure. Okay. Yeah, that's it. So manifold learning is something. Basically, manifold is a connected region. This is a niche concept. It is not as widely used as some of the other things here. And again, this comes under machine learning basics, and we shall come back to this concept later in the book, as it says here. And that concludes machine learning basics. Well, that was quite big. So next we will go to part 2, deep networks, consisting of modern practices. So far we have been learning stuff that has been since at least 2 decades. So everything we learned so far was present for at least 2 decades. That's quite old, isn't it? So lots of new stuff to learn. You have deep learning research. That's the next step. We want to go in depth. I mean, the next part would be deep networks, modern practices. We have completed all these chapters now. So that's it then. We shall meet in the next video, hopefully, if I make it.